Hello, my name is Birring, and today's lecture will be on eddy current inspection of non-ferromagnetic tubes. So non-ferromagnetic means materials like stainless steel 304, 316, Inconel 600, brass, copper nickel tubes, and the main uh, applications of this inspection is going to be in the petrochemical plants, for air conditioning chiller tubes, for the steam generators in the nuclear power plants. So those are the three major applications, petrochemical plant and steam generators being big ones. So what I will do is I will go through this whole process, and let's take an example. Let's say we have to do stainless steel tubes, heat exchanger with stainless steel tubes with a diameter of 3/4 inch OD and a thickness of 0.065 inch thickness, which is very common, one of the very common tubing you will encounter in the petrochemical plants. And another one will be the brass tubing. So first thing is that when we start, we have to make sure that we have a calibration tube has to be the same material and the same size. So if we are going to do that, then I have this calibration tube which is 3/4 inch OD and 0.65 inch in thickness, so it has to be the same. And this calibration tube should have those 5 holes, which is the 100%, 80%, 60%, and 40 and 20. So these are the flat bottom holes, and the size of these holes is given in the ASME section 5. Means that the depth is, I gave you the depth, but the diameter is given there, and the diameter is given in such a way that it produces the same amplitude from the holes. So as the holes get shallow, the diameter gets bigger. And now when we start with this inspection, we have to select the probe. The probe has to be 0.04 inch less than the ID of the tube. So whatever is the ID, not the OD, ID minus 0.040. So in this case, the ID is 0.75 inch, OD minus 2T, that's going to be 0.75 inch minus 2 times 0.065 inch. And the ID of this tube is 0.620 inch. So based on that ID, the probe size will be 0.620 inch minus 0.040 inch, which comes out to be 0.580. So you would need a probe, a bobbin probe with the size of 580. And the bobbin probe, here is it. And this is a 580 probe. The size of this probe is 580. And this probe goes right into the calibration tube, and there is some clearance of 40 mils, which is good enough to do the inspection. So remember, when we select this probe, we don't go by the fill factor and all that stuff. We go by this 40 mil clearance. So then the probe, there are 3 types of bobbin probes. There's low frequency, medium frequency, and high frequency. In this case, the frequency when I calculate will come out to be around 100 to 200 kilohertz. So we will use a mid-frequency probe with a diameter of 580. And that probe is, again, I'll show it to you. It's right here. And that's what it looks like. It has 2 coils which actually can operate in the differential mode or in the absolute mode. So this is 2 coils right here. And the probe length is about 50 to 60 feet long, so that it can be inserted into the heat exchanger tube. So this is the probe, and what I have here in this calibration tube is I've put a support ring here because we have supports in the heat exchanger. So in this one also I made a support ring here to produce a signal from a support. So now we have the probe, and then the next thing is that the instrument has to be special. These are multi-frequency ECT machines which have 4 frequencies, and they have capability to save the data and also do the analysis to calculate the depth of the indications based on the depth curve. So now the next step is to calculate the frequencies for this inspection, and we have to go with the 4 frequencies. The prime frequency, which is called F1, is a 100 and it's called F180, which produces a spread of 180 degrees, and that frequency is going to be 10 rho over T square, and it's an empirical formula. So rho is the resistivity in micro ohm centimeter, T is the thickness in inches, and so this 10 times 72 micro ohm centimeter for the stainless steel divided by 0.065 square, the thickness of the tube, and that comes out to be 170,000 hertz, so which is 170 kilohertz. So that's my prime frequency, which will produce a phase spread of 180 degrees on those calibration holes. Then we have to select second frequency F2. This should be half of F1, so that will be 85 kilohertz, and then F3, F1 over F4, and F4 is my discrimination channel, which should be about 1/10 of the prime frequency. The discrimination channel is used when we have a question whether this indication is real or caused by some kind of a deposit, and then we use it to actually discriminate between those types of discontinuities. And now F1 is going to be used to create the depth curve, and F2 is used to mix with F1 to create a mixed frequency to mix out the support plate. What does the mix mean? Mix means that you take two frequencies, F1 and F2, and F1 will produce a signal from the support like a figure 8, and F2 will also produce a signal like a figure 8. So what the machine, the ECT machine does is that it holds F1 signal and it takes the F2 signal and it rotates it and makes it equal and opposite to the signal from F1, so that when you add it, which is called the mixed channel, which is the additive channel, you get a zero response from the support plate. So that's the reason to use the mix, is to get the support plate signal down to zero, so that you can find the discontinuities or the pits or underneath the support plate also, because you have to inspect 100% of the tube length. Then we do the calibration. Okay, so now the calibration, which is the depth curve, should be created on the F1 frequency, not any other, not the F2, because the F1 will give you a phase spread of 180 degrees. And so what we do is we get the signals from the 5 calibration holes, and we have to set the 100%. So we have 100%, 80, 60, 40 and 20. So 100% is set to the 40 degree angle. So when 100% is set to 40 degrees, the liftoff will actually be about 0 degree automatically for the F1 frequency. So then once we have this 100%, we get the signals from the 80%, 60%, 40% and 20%, and get the phase angle of each of these signals, and the ECT instrument will actually make a depth curve on the F180 differential channel, and it's going to be looking like this. At 100% is 40 degrees, then 80%, whatever is the angle, then 60 and 40 and 20. And you can see that it creates a phase spread. It creates from 40 degrees to 180 degrees. So this is really the OD flaws. And then we connect this dot to the 0, and these become our ID. So ID is here. So ID, we don't have any reflectors, we just connect the dots. And so that if suppose we have 20 degree angle, we will say it's 50% ID flaw. So that's how we do it. So this is the ID line, and that's the OD curve. Now then we have the absolute. We use the absolute for the wall loss. And so for the absolute, what we do is we use the F2 channel, which is this F1 divided by 2, 85 kilohertz in this case. And that would actually, what we do is we don't set it to 40 degrees. What we do is we set the lift off to 0 degrees. So and then we get a signal like this. So absolute used for wall loss, F2, and set the lift off to horizontal. So this is how you actually do the calibration, and then the final display will be on the ECT machine, and let me show you that on a different board. So the final ECT display on your multi-frequency eddy current machine should look like this. You will have 2 impedance planes and 4 strip charts. That's the option you should select because there are many options on those machines. The 2 impedance displays that I use is the differential F1 and the absolute F2 for the wall loss, and this is the impedance. And for the strip charts, I use differential F. Now we are using only the vertical component. See here, V means the vertical component, which is the signal going up, and here it's going to be differential F1, and this will be differential F2 vertical, and this will be absolute F2 vertical and mix vertical. So as you can see that we see the support plate signal here on these channels. This is a support here. On the absolute it goes only one direction, which is right here. And then the mix, you will not see the support. So mix is going to be kind of like this. So that's how you set it up. This one actually I can remove it, but I just wanted to show you the signal, representative signal. So it's a process. This tubing inspection is a process, and it has to be done the right way to do a good inspection, whether you're doing stainless steel or brass or in canal tubings or titanium in the condenser tubes. So it's a wide range of applications, and if you do it right, you will actually get very good inspection of the heat exchanger tubes, 100% length. And thank you very much. Thanks for your attention.